Welcome to lecture number 6 for ECE 321 Analog Electronics, Electronics 2. Today we're going to look at calibration and noise. Now in the previous lecture we looked at different types of sensors you can come up with. I can come up with a circuit where the voltage is related to the temperature, replace the thermistor with other devices. I can have voltage related to magnetic field strength, flux, light, strain, your pick. Once you get that, how do I convert voltage into what I care about, in this case temperature? That's calibration. Now a couple definitions first. For a calibration function, the accuracy is basically the average error between the data, the dots, and your curve fit. The precision is basically the spread, or the standard deviation between the data and your curve fit. Ideally, I want to have a sensor that's both accurate and precise. On the first one, I have a sensor which is neither accurate nor precise. Basically, it's just random guessing. If I have a sensor which is accurate but not precise, on average, it's dead on, but there's a lot of variation in it. If I have a sensor which is precise but not accurate, the standard deviation, the spread, is constant, very small, but the average difference is large. Given a choice, I'd rather have precise than accurate because I can sit there and adjust, add a constant to it to make it both precise and accurate. What you want is accurate and precise. On average, it's dead on, and there's very little spread, very small standard deviation. So there's a couple different types of calibration. There's theoretical calibration. Given the sensor, I know the relationship between temperature and resistance. Given my circuit, I know the relationship between resistance and voltage. Going backwards, I can sit there and calculate the temperature based upon the voltage. That's theoretical calibration. Endpoint calibration is you have your actual data, the orange curve, come up with a straight line that passes through the two endpoints. That's endpoint calibration. Nice thing about endpoint calibration is it's easy to calculate. I've got two equations, two unknowns I can solve. But as you can kind of tell, I could do better. This isn't accurate, it isn't precise. Zero-based calibration is I force my calibration scheme, the blue line, to go through the origin. Sometimes I want to do that. For example, if I want to say resistance is the function of voltage and I use a voltage divider, I know that when R equals 0, or V equals 0, R equals 0. So I could force the data to pass through the origin. That's zero-based calibration. And then linear calibration is I've got a straight line, find A and B, what A and B, minimize the mean error and the variance of the error. That's linear calibration. Now to come up with the different curves, there's several ways to do it. A common way is least squares. Given a function or data, where I've got my x and y, basically voltage and temperature, come up with a curve fit so that my estimate of temperature is based upon some function of voltage, and for least squares this needs to be linear in the unknowns, linear in a, b, and c. Least squares then finds your constants a, b, and c to minimize the sum squared difference between the data and its curve fit. The nice thing about least squares is it does have a solution. That's a big plus. And the answer is usually pretty reasonable. The way you come up with the answer is you have the output, say temperature, is a linear function of what you know, say voltage squared, voltage in 1. This is your basis function. Depends upon your curve fit. If I want to do a parabolic curve fit, say I want it to be AV squared plus BV plus C, then my basis would be V squared, V, and 1. And my constants are A, B, and C. Now when I do this, oftentimes you have more data than unknowns. If I just had 3 equations, I'd have 3 equations, 3 unknowns, take the inverse, solve for A, B, and C. If you have more equations than unknowns, I normally can't invert B, or I cannot invert B. It has to be square matrix to invert it. So the trick is multiplying the left by B transpose. That makes this a 3 by 3 matrix. I can usually invert 3 by 3 matrices. Multiplying the left by B transpose B inverse, and I get A. So this is the solution for A. That turns out to be the least squares curve fit, B transpose B inverse, B transpose Y. And we'll go through a couple examples in a sec. Just for completeness, there is a thing called weighted least squares. If I want to weight the data differently, what I do is take my equations, multiply on the left by Q. Q is my weighting, such as if the weightings are 1, 1, 1, 10, the third data point has a weighting of 10, all the rest of the weightings are 1. Multiply on the left by B transpose. Now invert B transpose QB. This is weighted least squares. So for example, let's take a voltage divider. Suppose I want to use this to be an ohm meter. I'm going to measure the voltage and from that calculate R. A theoretical calibration would say that R is equal to, in this case it's going to be V, is going to be V over 10 minus V times 1K. That's theoretical calibration. A linear curve fit would say, let's come up with an equation. R is some function of V. And if I plot the voltage, what I know, versus resistance, as R goes between 0 and 1,000 ohms, I get this curve. Come up with an equation to approximate that function. This is what it exactly is. Can I come up with a simpler equation that's close? Well, with zero-based calibration, I would let R be A times B, so that when B equals 0, R equals 0. Come up with A. Well, here the basis function is just V. Doing least squares curve fitting, that would be A is the inverse B transpose times B times B transpose times R, what I know. I'll wind up with A is 169.53. So the red line is my curve fit. Note that it passes through the origin. It also minimizes the sum square difference. Take the difference between these two, square it, add them all up. This line minimizes the sum square difference, least squares. So there's my answer. In terms of accuracy and precision, the accuracy would be the mean error, R versus my curve fit, B times A. So it's not accurate. The precision is the standard deviation. Second problem. Let's do endpoint calibration. Just using the two endpoints, I get two equations, two unknowns, solve for A and B, and you wind up with R is 200V plus 0. And note that this passes through the left endpoint and the right endpoint. In terms of accuracy and precision, again, the mean error is actually worse. The precision is worse. Likewise, least squares is the best you can do, given 1 degree freedom. Endpoint doesn't care, it just forces it to pass through the two endpoints. Can I do better? Well, that'd be linear calibration. To do R equals AV plus B, choose the basis to be voltage and 1. One way to generate the number 1 is anything to the 0 power is 1. Now solve for A using least squares. I get 201 minus 118. So here's the straight line that minimizes the sum squared difference between the straight line and your data. So that's the best you can do on a least squares sense. And sometimes this doesn't make sense. For example, this says I have got negative resistance when V is low. That's why sometimes you want to use zero-based calibration. But if I don't care about that, that's the best I can do. The accuracy, this is dead on. On average, the error is 0. The precision isn't 0. There's a difference between the two. So this is a sensor which is accurate but not precise. Can I do better? Well, if I use a polynomial curve fit, like approximate this with a parabola, I can. So let's use the basis to be V squared, V, and 1. Now recalculate A, and what I get is 27V squared plus 52V plus 24. That gives you the red line. And notice that once again the accuracy is 0, the precision is much smaller. So this is a better curve fit. And if I add more and more terms, I can get more and more accurate. That's basically calibration. Take something that you can measure, like voltage, and from it, tell me something that I want to know, like resistance. Or for various temperatures, or various sensors, I could find temperature, light, strain, pressure, flow, whatever. So in summary, in terms of calibration, there's a couple different schemes. For zero-based calibration, I have the basis just being A times B. Endpoint calibration, I make a pass through the two endpoints. Linear calibration, I free up both A and B. What's the best I can do given 2 degrees of freedom? Polynomial, what's the best I can do given 3 degrees of freedom? And once I free these up, the accuracy error becomes 0, the average error is 0. And as I add more and more terms, they get more and more precise. So that's really the idea of calibration, is just curve fitting. Take something that you know, like voltage, and calculate something that you want to know, like temperature, resistance. So here's a problem. Come up with a circuit to approximate this. And the circuit is linear, so come up with a straight line to approximate that. And let's take a short pause and let you come up with the answer. So starting out, what I would do is come up with a straight line to approximate this data. So if that's my straight line, I want to say y equals ax plus b. This line isn't the least squares line, but if you eyeball it, it's usually pretty good. So let's just take the endpoint calibration. I want to go from when x is 1.4, I want y to be 10. When x is 4.3, I want y to be minus 10. So I can find the slope, a, as change in y over change of x. The output changes by 20, as x changes by 2.9. So 6.89. So y is negative 6.89 x plus b. To find b, plug in a point. When x is 1.4, the answer should be 10. So this gives me minus 9.64. So I need to add 19.64. So there's my equation. That's my curve fit for this line, or my calibration function. If x is equal to 2.5, I can find out what y is. Y from the graph is actually 4. From my curve fit, I would have 2.5 times 6.89 plus 19.64. My curve fit says 2.41, it should be 4. That's the calibration error. And then to design the circuit, I want to have, this has the negative gain, so here's x, goes in the minus side. I would rewrite this as y is 6.89 times 19.64 divided by 6.89, 2.85 minus x. Yeah, same thing, just rewritten. But that works better for this guy. The gain is 6.89, so 6.89k, 1k, 6.89k, 1k. This is an instrumentation amplifier. Gain is 6.89 times A minus B. A is 2.85 volts, and B is X. So this circuit implements that curve fit. Okay, switching topics. With noise, ideally you want to have a circuit with no noise on it. Noise is, if you ever looked on the oscilloscope, I've got a signal like this and there's a bunch of fuzz on it. That's noise. Where noise comes from is sometimes if I have a resistor, due to Brownian motion, there's a certain chance more electrons are on one side than the other. That produces noise. The other way, if I have long wires, these wires act as antennas. The antennas also pick up noise. Here's the problem. Suppose I've got a sensor a long way away, like at the top of the smokestack. I want to measure the temperature at the top of the smokestack and keep the noise down. How do I do that? Well, there's a sensor over here. I'd like to have the output just be proportional to the sensor noise without any noise, or to sensor signal. Before we start, let's do a couple definitions. If I have an amplifier, there's a common mode gain. I've got the plus and minus. The output should be gain times the difference in the two. That's the differential gain. There's also a small gain proportional to the voltage. That's the common mode gain. Typically, the differential gain is much higher than the common mode gain, and the ratio is the common mode rejection ratio. Ground loops, those produce noise. Essentially, all grounds are not equal. If I have two different points grounded, then I'm going to be getting current because there's a slight difference in voltage between the two. That's called a ground loop. One trick that I do is if I'm ever in a presentation and totally lost, if they're dealing with hardware, I would ask how they take ground loops into account. Now that we can kind of sound intelligent. An example of a ground loop is back in Ohio. They built transmission lines going between the Ohio River, where the coal plants are, and cities like Columbus. The neutral ideally should have no current on it. If there is current, that's an indication of a fault on one of the lines. Well, when they put in the transmission lines between Columbus and Cincinnati, they got current on the neutral line, and that was causing the breakers to trip. Couldn't figure out what it was. Well, it turns out actually Cincinnati is about 4 volt different than Columbus. So when you short the two together with a wire, you get current. That's two different places have two different grounds. If you ground both of them, I get current on the ground line. The signal to noise ratio is the ratio of the signal to the noise. Ideally, you want that to be as large as possible. So let's look at how you would put a sensor some distance away, say on top of the smokestack. One approach, the approach that's actually the worst, is if the smokestack I've got to ground, at the amplifier I've got to ground the 2 points. That's bad. This is kind of like Cincinnati and Columbus. I ground Cincinnati, ground Columbus. What's going to happen is these are different voltages that produces current. A way to analyze it is I've got the two different grounds. There's the voltage between the two grounds. I've got the wire. The wire picks up signals as an antenna. The total voltage then will be the voltage of the ground difference, plus the signal, plus the wire. So the output is related to your signal, but there's a bunch of other noise on top of it. That's about the worst way to connect a sensor to an amplifier. A better way is to only have a single ground. What that does is this ground no longer matters, the difference between the two grounds. But what I get is basically this is a big loop antenna. The voltage produced by a loop is proportional to the area times the magnetic field strength, the electric field strength. A larger area makes a better antenna. So what I'm going to get is the voltage on this wire as an antenna, plus the signal, plus the voltage on that wire. So I get a lot of, these kind of cancel. I get a lot of voltage due to the area as a loop and antenna. Better option. Take the two wires and twist them. What that does is that keeps the area really tight, very small. So I have less Faraday noise due to Faraday's law. Plus they cancel. So if I have a plus, minus, these all cancel out. So ideally there should be no voltage between the two. There will be a little bit because I got some area right here and a little bit of area right here. But twisted pair is actually a really good way to keep the noise down. And if you notice, quite a few wires are twisted pair. I'll still get a little bit of noise, but it's much, much better. The best case is shielded twisted pair. I've got a twisted pair, which got rid of pretty much all the electric fields going between these 2 points. If I shield it, that shielding makes the electric field almost zero. Then whatever's left over is canceled. Shielded twisted pair is the best and probably most expensive cable you can use. Problem with the shielding. Where do you ground it? Well, the worst thing you can do is ground it at both B and D. So if the amplifier is grounded, I don't want to ground it over here. That gives you a ground loop. The best case is ground the shield right here, so I only have a single ground, or ground it right here at the amplifier. There's a small wire right there. C is actually a little bit better than D. These are about the same. Worst thing you can do is ground it at 2 points. If I have a sensor which is grounded, then what I want to do is take the shielding and ground it at the sensor where it's grounded, or short these two together. A is best, B is pretty close. What I don't want to do is have 2 grounds. That creates ground loops. Don't ground it at C or D. So where the grounding is important is if I have a signal with noise, one way to get rid of it is to filter it. Filters are band-aids. A filter filters the signal as well as the noise. The hope is that if the noise is everywhere and the signal is at low frequencies, I can build a low-pass filter which slightly distorts the signal but greatly diminishes the noise. That's a band-aid. Better is to not have noise in the first place. To get rid of the noise overall, typically use twisted pair shielded wire if you can afford it, or twisted pair if you can't afford it. And make sure there's only a single ground. You don't want ground loops. So in summary, you've got calibration and noise. Calibration is basically how to approximate a function with a line, a parabola, or some other function. Least squares is a pretty common way to do it. You've also got noise on your sensors. To get rid of noise, avoid ground loops, use a single ground, use twisted pair, or better yet, use shielded twisted pair. If all else fails, use a filter, but really filters are better to be avoided if at all possible. A filter is a band-aid due to bad connections. So use one of these if you can. So that should be enough to get you through the homework on calibration and noise. And that's lecture number 6 for ECE 321 Analog Electronics.